nanoHUB-U, online instruction.
Hello, and welcome to the nanoHUB-U course, The Physics of Electronic Polymers. My name is Brian Baduras, and I hope to walk you through a few different examples throughout the entirety of this series, and we'll start in the first lecture and talking about molecular weights of polymeric materials. In particular, today we have two learning objectives, and those two learning objectives are to define, in more or less a phrase sense or a word sense, what we mean by a repeat unit in a polymer chain, what we mean by number average molecular weight, what we mean by weight average molecular weight, and what we mean by dispersity of a polymer. Then hopefully what we'll be able to do is calculate those values that we're talking about now. And this is a very important property in polymer science. That's why we're starting out with this foundational lecture here, because we'll use this throughout the entirety of the course. And this is because we have typical molecules when we think of organic chemistry or chemistry in general. And one typical example of that is benzene. Here we show a picture of a benzene bottle. And when you look at this bottle, it has a lot of information on it. And one of the key pieces of information that is on this bottle is the molecular formula. And if we zoom in on this molecular formula, we'll see that for benzene, we have C6H6 as the molecular formula. Okay? And that's because every molecule in this bottle of benzene has 6 carbons and 6 hydrogens. Now for polymers, if we had a bottle of polymer on the counter, this wouldn't necessarily be the same. In fact, polymers have what we call repeat units, or little units that make up the entirety of the polymer chain. And inside that bottle of polymer that you have, there's a very high likelihood that not all the polymer chains, all the polymer molecules, have the same number of repeat units. Okay? We're going to define a repeat unit or show it schematically as this little blue symbol here throughout the rest of this lecture. And you can think that when we have this polymer, one term we use is the degree of polymerization. And the degree of polymerization tells us how many of those repeat units we have. So for instance, here when we have an 8 mer, we have 8 repeat units. This 16 mer will have 16 repeat units, and this 21 mer will have 21 repeat units. So we'll have a degree of polymerization of 8, of 16, and of 21. Once we know how many repeat units we have, we can start thinking about what the molecular weight of the material is. Okay? And by knowing what the molecular weight of the material is, that'll tell us a lot about what the physical properties are, especially when it comes to electronically active polymers. So the number average molecular weight that we talk about, it provides a measure of if we picked a polymer chain at random out of our bottle of polymer, what's the likelihood we would get a certain molecular weight of material. So let's pretend that we had 4 different chains in our series. We had 1 6 mer, we had 2 10 mers, and we had 1 16 mer. If that's what we had there, we could think about the idea of how likely are we to pull a 16 mer out of this bottle. Well, there's 4 chains, and there's 1 16 mer, so we'd have a 1 in 4 chance of pulling out the 16 mer. In a similar manner, we have 2 10 mers, and we have 4 chains, so we have a 50% chance of pulling out the 10 mer. So really, the probability of pulling out one of these chains is the same as the mole fraction of those chains. And we can write the mole fraction, xi, is just the number of imers we have. So for instance, this would be 2 for the 10 mers, divided by the total number of chains we have, in this case 4. We also know that each one of these repeat units has some kind of mass, m0. So this would be the molecular weight of the repeat unit. And thus, the molecular weight of one of these chains, m sub I, is just the number of the imer you have. So in this case, for instance, a 10 mer times the molecular weight of a repeat unit. So the molecular weight of this chain is just 10 times whatever m0 is. And let's take m0 to be 100 grams per mole in this case. So now we can calculate mi. We know what a 6 mer is, we know what a 10 mer is, we know what a 16 mer is. We can calculate the number average molecular weight just by summing up xi times mi. And you can rewrite this and do a few mathematical manipulations, but this is just the molecular weight of a repeat unit times the summation of the number of repeat units in the material times the number of polymer chains divided by the summation of all the polymer chains. And that's the number average molecular weight, and we symbolize that by Mn. Another way we can think about molecular weight is not to say what's the likelihood of pulling out a single polymer chain, but what's the likelihood of pulling out an imer. And that's called the molecular, or the weight average molecular weight. So now, if we have a repeat unit of a given molecular weight, we can say, what's the likelihood that I'm going to pull out this particular repeat unit right here? Now, there's more repeat units on a 10 mer than there is on a 6 mer, and there's more repeat units on a 16 mer than on a 10 mer. So we're going to have a higher likelihood of pulling out an imer on one of the longer polymer chains. So we're going to weight those more. And the way we do this is to take the weight fraction now. Instead of the mole fraction, we're going to take the weight fraction. But in a very similar manner, we're going to go ahead and say that the weight average molecular weight, M sub W, is just the weight fraction times Mi. And again, we can manipulate this in a different manner and just say that that's M naught times the summation I squared Ni divided by the summation I Ni. And if we go ahead and do that for our 6 mer, our 10 mer, and our 16 mer, with an assumption of a molecular weight of a repeat unit of 100 grams per mole, we'll find that that number ends up being 1171 grams per mole. The last thing we want to talk about is the differences between these kinds of molecular weights. And the one way that we quantify these values is through a term called the dispersity. And the dispersity is defined to be the weight average molecular weight divided by the number average molecular weight. And this number comes into play in the idea that, remember, MW is always weighted towards those larger molecules more. So MW is always going to be greater than or equal to MN, thus the dispersity is always going to be greater than or equal to 1. So the closer you are to 1, the more uniform a polymer mixture is. And you can summarize that by the idea that the dispersity can kind of be thought of as the standard deviation, or sigma, of the material. And you can actually calculate it that it's just the number average molecular weight times the dispersity minus 1 to the 1/2. So if you have a true dispersity of 1, this becomes 0, and you have completely uniform chains. And that's what we think of when we talk about a bottle that has a bunch of polymer in it. How dispersed is it? How many short chains do we have? How many long chains do we have? Because that'll impact what our final properties of the material are. Now today we've talked a lot about molecular weights, and this is one way to quantify the size of a polymer. In the next few lectures, and what I hope you come back for, is the idea that we'll talk about not how to quantify the molecular weight, but how to quantify the spatial extent of the polymer. So we'll talk about how these big long spaghetti strings, if you will, can be thought of as how they occupy space. So I hope to see you next time on the nanoHUB-U course, The Physics of Electronic Polymers.